Everyone. Thanks for coming today. Very excited to have Dr. McKenzie Kuhn with us from the University of British Columbia. I'm Kyle Arndt. I'm at the Woodwell Climate Research Center and a co-lead in the Permafrost community of practice for IARPIC. We have some fellow co-leads here as well, John, Lauren, and Ava, from what I can see here. Yeah, and we're really happy to have Kenzie here presenting her work that's really stemmed since her PhD work at the University of Alberta on BAWLD, the Boreal-Arctic Wetland and Lake Dataset. So not only giving us a really good land class and wetland class database for the Arctic Boreal region, but today we're also excited to hear about her work using that to help us better understand natural methane emissions from these ecosystems. So with that, I won't take up too much time and I'll let Kenzie take it away here.
All right, everyone can see my screen as I have to ask as we're on Zoom,
Yeah.
per the ritual. Well, thank you so much, Kyle, for that introduction, and thank you to the whole IRPIC team for inviting me to talk. As I was preparing for this talk, I was going into my IRPIC profile, which I realized that I set up during the first year of my PhD in 2017. So I had to do a little bit of updating in the profile, but it felt like a really kind of fun full circle moment to um, come give this talk today and talk about a lot of the research that really stemmed all the way back in 2017. Um, so I shortened the title of my talk today just for space for this title. But really, I think Kyle did a good job of introducing kind of the key aspects of the work that I started with also many collaborators. I see a few of you are on the call today, so hello. And so yeah, I thought I would kind of jump right into it. I wasn't quite sure. Oh, sorry. Let me start first with my land acknowledgements. So um, I'm presenting today from you, or to you, from the traditional, ancestral, and unceded territory of the Musqueam people in the landscape known as Vancouver, British Columbia. And I also want to acknowledge that, I'm presenting, work that comes from a data synthesis. So there are a lot of data presented that were measured and took place on kind of many indigenous lands across the Boreal-Arctic region. So I'm incredibly grateful to those communities for working with and sharing their knowledge with myself and many of the other researchers who contributed to this synthesis work. So this might be a little bit of a review for some of you, but I wanted to start just kind of with the general background knowledge of, why methane emissions and why wetlands and lakes. Well, methane emissions from wetlands and lakes are globally significant. So this is a wonderful graphic that many of you I'm sure have seen from the Global Carbon Project that really puts wetland and lake methane emissions into context of anthropogenic emissions. So wetlands and other natural emissions, which includes lakes, are shown here in these green arrows. And we can see that they're comparable to emissions from, for example, fossil fuel production and use, as well as agriculture and waste. And really what I want to mention here is that northern ecosystems make up a substantial portion of these global wetland and lake emissions. However, kind of our estimates of that contribution from northern ecosystems are still quite variable and really uncertain. Um, and so I've spent a lot of my work, and I know a lot of people on this call have also spent a lot of their time trying to constrain northern methane emissions because our ability to kind of better constrain current emissions will also help us predict changes in future emissions. Um, and so why focus on the north? Well, lakes and wetlands are abundant throughout the region. I know many of you are based in Alaska and are really familiar with this. So this is an example of a permafrost peatland complex in the Northwest Territories. And we can see the diversity of this ecosystem. And really the key point that I want to highlight here is that these wetlands and lakes and the soils and sediments therein store about 1/3 of the world's soil carbon. So there's just a lot of carbon in the north. And a lot of this soil carbon is held up in permafrost. And as the climate warms, these permafrost landscapes are changing. So we now know that the North is warming at a rate almost 4 times that of the rest of the world. And so permafrost thaw is really altering the physical landscape, and also its related biogeochemistry, which can have multiple consequences when we're thinking about greenhouse gas budgets and the methane budget in particular. Um, and so I just wanted to highlight some of the kind of key trajectories of permafrost thaw and its impact on the carbon cycle and methane in particular. So this is a diagram from Ted Scher. It's a very classic diagram from one of his 2015 papers. And it really highlights the kind of the two key trajectories that can happen upon permafrost thaw. So if we focus here to the left, this scenario highlights what happens when permafrost thaw happens, and that leads to soil drying and, for example, lake drainage. And under this scenario, kind of one of the key consequences is the emission of carbon dioxide. However, we can also have permafrost thaw trajectories that lead to wetter or more saturated environments. For example, the development of wetlands or thermokarst lakes. And under these scenarios, we not only get the emission of carbon dioxide, but also methane. And so I wanted to take us a few steps back and first talk about how do we measure greenhouse gases across the landscape. And one of the most popular methods, especially increasing lately, are eddy covariance towers. So this is a method that can measure methane and carbon dioxide from what we call kind of a larger footprint across the landscape. And even more common is the use of chambers or chamber measurements that can be either attached to portable greenhouse gas analyzers, or if you're really old school, you can take a syringe measurement. And these can sometimes simply be even just like a Home Depot bucket, equipped with a pool noodle so you can float it on top of a lake. If you're based out of Canada, this is actually a Canadian Tire bucket, but pretty similar. And a lot of my work focuses on these chamber measurements, which can give you a really detailed sense of the factors that contribute to methane emissions. For example, the soil carbon, the saturation, and the vegetation that can be contained within these chambers. And as a community, we've been measuring methane fluxes using these chamber-based methods since the 1970s. So here I'm showing the number of flux sites across the Boreal-Arctic since those early measurements, and we can see that the number of sites that are being measured has really grown exponentially. And so have our techniques that we've developed to measure these fluxes. So this is a photo from a colleague and a collaborator, Patrick Krill, and it's showing essentially one of the first chamber methods at a northern site in northern Sweden. So these original measurements taken in 1970 were done with this essentially tin can with a hole at the top. And in the backdrop, we can see these more sophisticated automated chamber measurements that now run at the site. So there's really a wealth of data and a strong trajectory towards increasing technology and number of measurements associated with that. And we have used these flux measurements to scale methane emissions across local, regional, or even circumpolar areas. And one common approach is what we call a bottom-up scaling method. And really, in its simplest form, you can think of this bottom-up approach as multiplying a flux by a known area. So these fluxes can represent either simple averages, and again, these are what we're measuring with, for example, an eddy covariance tower or a chamber. Or these can be more complicated statistical models where you can relate methane flux to, for example, water table or temperature, vegetation. And these fluxes can also represent process-based models, which are more of a mechanistic insight to fluxes that are informed and kind of bounded by the in-field measurements. And the areas, these can be either kind of static maps, so unchanging maps with the areas of wetlands or lakes. They can be more dynamic, for example, seasonal wetland maps, and they can represent local, regional, or even kind of circumpolar areas. So you can really think of this bottom-up approach as the name states, so kind of working from the ground up to arrive at these methane budgets. And often we compare these bottom-up estimates to a technique known as top-down. And so top-down approaches use atmospheric inversion models and chemical transport models to essentially look at the concentration and the stable isotope signature of methane in the atmosphere and essentially work backwards from those chemical signatures to build the budget from the ground sources. And now I bring up top-down estimates because when we look at bottom-up estimates of methane emissions from lakes and wetlands, which I'm showing here, so on the Y we have annual emissions, and then we have bottom-up emissions from lakes and wetlands. And really when we add them together, we see that this bottom-up approach tends to have 2 to 3 times higher annual methane emissions than what is estimated from top-down approaches. And this mismatch grows even larger when we consider other aquatic sources, such as rivers, for example. And so a lot of my work focuses around how do we better constrain these bottom-up emissions so we can kind of start to reconcile some of these differences. So why the mismatch? One of the main, or one of the, I say, key hypotheses we have for the reason why we see such a large mismatch really has to do with kind of this history of scaling methane emissions for different ecosystems separately. So here I'm showing annual emission estimates on the Y and the publication year for wetland, lake, and river annual methane emissions. And here we can see that they are often done in separation, and really few studies include all of these ecosystems and their methane emissions together. And one of the reasons why this can be potentially problematic is because we tend to not have a uniform system of classifying our wetlands and our lakes in these various ecosystems. One example I love to give is this example of these small lakes or open water wetlands. So in some countries, this might be classified as, for example, an aquatic ecosystem or a pond. But in Canada, these ecosystems are usually grouped with wetlands. And this is important because how we define these ecosystems also defines how we map them and how we develop these maps. And so kind of without these uniform systems of classification, often what can happen with these more kind of ambiguous systems is that they can be included in both wetland and lake scaling efforts. So if you're scaling wetlands and lakes separately and then you add them together, it can lead to this phenomenon that we call double counting, essentially. So potentially attributing higher methane emissions than would occur if we had kind of more of a cohesive land cover classification system kind of going into our maps and our flux measurements. Another reason potentially for this mismatch is that kind of historically, when we're looking at scaling methane emissions from wetlands and lakes, the land cover classes have been coarsely grouped. And what I really mean by this is that kind of historically, wetland methane emissions have been done for either kind of one wetland type or maybe two or three. But we know that methane fluxes are influenced by kind of a swath of environmental factors. For example, is there permafrost, like in raised permafrost bogs that lead to drier, less saturated ecosystems and lower methane emissions? What is the organic soil like? What is the water table like? Are there vegetation present, for example, sedges? And the same can be said for lakes, which methane emissions are really dependent on the type of organic sediment, the permafrost composition, and the size. So if we don't account for this variability in methane emissions across the landscape, we could be kind of misattributing methane sources. And so this brings me to the work that I started during my PhD. So we developed the Boreal-Arctic Lakes and Wetlands Dataset, also known as BAWLD. We workshopped a lot of ideas, and believe it or not, that was the best one, perhaps. And so BAWLD is a uniform system for identifying wetlands and lakes for land cover classification and flux distributions, really with the ultimate goal of scaling methane emissions. So there are two components to BAWLD. The first of which is a land cover distribution map. This was led by my PhD supervisor, David Olefelt, out of the University of Alberta. And this map uses kind of available geospatial data layers, for example, soil maps, wetland distribution, so on, and expert assessment to essentially attribute kind of percent cover of various wetland, lake, and upland ecosystems to a gridded product, which I'll talk about a little bit more. And this map is accompanied by a methane flux dataset that uses the same classification scheme. So the wetland classes and lake classes that are available in the map are also used to designate kind of flux landscapes in this synthesis. So what are the different lake and wetland types? So we have 5 different wetland classes that are defined by permafrost presence, hydrology, so for example, water table, as well as vegetation. So are they sedge dense, for example, like in a marsh, or more sphagnum dominated, for example, in bogs? And we also have 7 lake classes that are split by their size and permafrost and organic sediment composition. Not shown here, we also have 3 river classes, and we include various upland classes such as boreal forest, dry tundra, and rocklands. And as I mentioned before, this gridded product is at the 0.5 by 0.5 degree resolution, and essentially within each grid cell, we provide a percent cover of each of the different landscapes. For example, it could be, 50% large lakes, 10% bogs. And when it comes to the flux data set, this is the first version of BAWLD methane or BAWLD CH4, and this data set includes over 550 wetland and upland sites where we essentially extracted the growing season averages for each of the different terrestrial land cover classes, including the 5 wetland classes. So map to the left, you can see their spatial distribution. Pretty good cover. And then this figure here to the right showing their flux densities. And so here you can even see the importance of having these various land cover classes. So a permafrost bog has typically much lower methane emissions than, for example, a tundra wetland or a marsh. And so here's really where we make our case that kind of splitting these land cover classes based on their methane emitting potentials is really important. Here we can look at the same figure, but for the lakes flux sites. So we have over 450 site year measurements. These are from essentially kind of what we call the open water season average. So usually these are summertime. And similarly, you can see the distribution of the fluxes, which we extracted both diffusive fluxes and ebullitive or bubble emissions. And really, we see the highest emissions from small, organic, rich ponds, and the lowest emissions from these really, really large lakes. And so what I'm currently working on and is almost finished for the co-authors that are in the meeting today was essentially combining these 2 products for this new bottom-up estimate. And so essentially what I did is I took the flux database and I developed a simple statistical model that includes land cover class and also the relationship with temperature. And we're able to multiply this model by the given class areas. And what is really, I think, kind of unique about our approach is that this model really lets us do 3 things. The first of which is it allows us to calculate current methane emissions. It also allows us to separate the uncertainty that comes from the flux database versus the uncertainty from the class areas or the wetland map. So we can kind of see which is more uncertain. And the way that we develop the model in the land cover classes, we can also test the sensitivity of methane emissions to various climate change drivers. And really the key ones that we wanted to test were the influence of increasing mean annual temperature and the influence of permafrost thaw, which can lead to essentially different changes across the landscape. For example, the conversion of elevated permafrost bogs to more saturated bogs as one example. So jumping into the results, what did we find? So for our current model estimates, we find that both for wetlands and lakes, our annual estimates are lower than previously reported or on the lower end. So we arrive at around 32 teragrams total of methane from wetlands and lakes. This doesn't include also additional emissions from rivers, for example, or soil uptake from boreal forests. And here I just want to remind you that fossil fuel emissions are close to around 130 teragrams. So this is a not inconsequential methane emission budget. And here to the left, we can also see the spatial distribution of where those fluxes are coming from. So kind of the highest emissions are from kind of the densest wetland areas. For example, the Hudson Bay lowlands in Canada, and the West Siberian lowlands in Russia, and then of course pockets of Alaska, for example, the YK Delta. And there is uncertainty or are uncertainties associated with these estimates that I'm going to come back to closer towards the end of the presentation. First, I wanted to spend a little bit of time on kind of how we developed our future emission scenarios and kind of arrived at these sensitivity analyses. So we have kind of three main climate change variables. The first of which is mean annual temperature. And for these future scenarios, we used the shared socioeconomic pathways or SSP scenarios 4.5. And we have essentially three emission scenarios, which we call low, moderate, and high. So going from kind of lower temperature increases to the highest. We can also manipulate the growing season length. And for lakes, this represents the open water season length. So the period of time where there is not ice cover when lakes are more likely to be emitting methane emissions. And then we can also, using the BAWLD land cover dataset, we can mess around essentially with permafrost thaw and different land cover transitions. So I want to spend a little bit of time on what these land cover transitions are for each of the different scenarios. So as I mentioned back at the beginning of the presentation with the figure from Ted Scher, is that there are kind of at its simplest forms, two main trajectories that can happen across the landscape with thaw. One of which is drainage and drying, and the other one is essentially wetland and lake expansion. So in our low emission scenario, we essentially say that with permafrost thaw, drainage area is going to be larger than expansion. For the moderate emissions, we say that these two factors are equal. And then in our high emission scenario, we say that drainage is less than expansion. So kind of the area of expanding wetlands and lakes is greater than the area that is kind of drained and drier than previous conditions. And so we can look at these three different factors, and we can also look at their interactions. So if you have a longer growing season, then that's going to also lead to kind of an amplified impact of permafrost thaw and land cover transitions and the amount of time that mean annual temperature can impact methane emissions. So here I'm going to show the results for wetlands and lakes separately. So this figure to the left is showing the change in wetland emissions from current. So if there was no change, all these bars would be at 0. And then each of the panels represents those low, moderate, and high emission scenarios. And then the different colors represent the different climate drivers that I just outlined. So in gray, we have the interacting effects. The blue represents the growing season day duration. The red is the mean annual temperature, and the black is thaw. So through these three emission scenarios, we find that future methane emissions, and again, this is to the year 2100, increase in our model from 20 to 40% from current. And really, this increase is mostly driven by a longer growing season duration. So more so than the impact of increasing temperatures and even thaw. And, really when I was kind of designing this model and kind of developing these hypotheses, especially early on in my PhD, I found it actually a bit surprising that this thaw component was not larger. And one of the reasons why we think that our models are less sensitive to thaw, at least in terms of increasing emissions, is because we allow the model to also account for potential landscape drying and drainage. So for example, if you have a permafrost wetland, like a wet tundra, that is underlain by permafrost, and that permafrost thaws, essentially you can allow for drainage of those systems, leading to kind of drier conditions that are less suitable for methane production. Here I'm showing that same figure, but for future lake emissions. Note the change in scale. So this goes to 6 teragrams, whereas the other one went to 12. Showing the same low, moderate, and high emission scenarios. And here with lakes, we find that in our future model predictions, emissions increase between 40 and 90% from current, so quite substantial. And opposed to the wetland models, we see that these changes are really driven by warmer mean annual temperatures. So within our lake model, emissions are highly sensitive to temperature. And moderate sensitivity to increasing ice-free days or the duration that these lakes are not covered in ice. And we also, again, here see minimal impact from permafrost thaw. And in fact, in our low emission scenario, when lake drainage is greater than lake expansion, we see that there's actually a reduction in emissions that can be attributed to thaw. Now, before I end my talk, I wanted to jump back to this idea of uncertainty because really what um, the model and the map allow us to do is assess these different sources of uncertainty within the same framework. And so here, what I've outlined are essentially all of the various components that went into the model, including the flux model and the land cover map. And I've listed them from essentially the highest sources of uncertainty in red to kind of more minor sources of uncertainty, so less than a teragram of methane per year. And there's a lot of text in here. So to the right, I pulled out a few select components that I think are worthy of discussion. So we see that some of the highest sources of uncertainty within the model framework that we developed include winter fluxes from wetlands. So as I mentioned earlier, the BAWLD methane flux dataset is really dependent on growing season emissions. So we only collected growing season measurements. And so we had to use a ratio of growing season to winter emissions from previous studies to arrive at annual emissions. And we see that kind of that fraction that you can attribute to winter fluxes is really important for annual emissions. There's also a high uncertainty associated from ebullitive emissions from lakes. And again, this also similarly comes back to the flux data set where the flux database that we had represented diffusive fluxes much better than it did ebullitive emissions. So our models that we were able to develop for ebullition did not perform as well as they did for diffusion. And I also want to highlight that moderate sources of uncertainty still include fen and tundra wetland areas. So kind of developing better wetland maps will also reduce the uncertainty of these annual emissions. And then the last one I wanted to pull out kind of just as a point of conversation is that dry tundra and boreal forest ecosystems. So these are ecosystems that are capable of sequestering methane from the atmosphere have also high uncertainty between 1 and 3 teragrams each. And even though this is lower than some of the uncertainty that I mentioned previously, these ecosystems make up about 80% of the area. And so constraining these uncertainties could also have a substantial impact on our overall uncertainty of these budgets. And then I'm almost done, but I just thought I would give a quick plug to some of the ongoing work that has stemmed from the BAWLD flux development and the BAWLD database. And so I've been super excited to work with Woodville Climate Research Center, and especially Anna Virkala, for the past about year and a half to combine the BAWLD methane dataset with some previous work known as ABC flux, which has looked at carbon dioxide flux observations. And so this new version of the flux database, ABC Flux version 2, will include both methane and carbon dioxide fluxes from terrestrial and aquatic ecosystems. And it includes these fluxes at a monthly time step, which is a higher temporal resolution than we had included previously in BAWLD. And so as part of this development, we've also expanded the number of sites. So we reached out to over 50. I think this number is actually even higher, somewhere towards 80 different researchers to ask them to contribute their data to help us expand this data set. And really, what I'm hoping to kind of look at moving forward with this new data set is kind of centered around this question of can monthly resolution data sets help reduce uncertainty? So here I'm just showing some of the preliminary results of the monthly flux distributions, for example, fens and wet tundra. And with that, I just wanted to say thank you. I have a lot of wonderful collaborators and colleagues who've been kind of helping me with this work since my early days of my PhD, and it's so close to being done and submitted, and we can move on to kind of the next component of this research, as well as a lot of wonderful funders, the Permafrost Carbon Network, who was really supportive of this synthesis work. And with that, I think I'll leave it on this slide because this usually gets the most questions, and open it for discussion.
Great. Thanks so much, Kenzie. Yeah, feel free to unmute yourself with any questions or use the raise hand feature, or you can also post them in the chat and we can get around to them as well for anyone that has any questions. Yeah, go ahead, Katie.
Hi, Kenzie. Thank you for the nice talk. It's good to see some more of these results coming together. I was wondering, what have we learned from, in the beginning, you talked about how people used to take a water sample from a lake and they would shake it up and they'd do an equilibration, and then they would assume that that represented diffusive emissions. And there are probably thousands of those data points in the database. Now we have these mobile chambers. Is it right to just add all that data together? What have we learned from using the mobile chambers? And in what ways maybe should we correct the old data sets?
Yeah, that's a great question, and it's obviously something I had to think about a lot. Is that the data that go into this database are very different, and they were collected at different times, often with different techniques. I think specifically for lakes, with especially like portable greenhouse gas analyzers and being able to use chambers and take more kind of like real-time measurements, so seeing it in the field compared to these kind of older methods where you collected a sample and had to bring it back to the lab and you wouldn't know for maybe a couple weeks like what the result was. I think really we see a lot of spatial variability across these lakes. And so really I think when it comes to the future of lake scaling and lake modeling, we need to figure out what does the spatial variability look like? Are there patterns across these different types of lakes, lake depths, lake sizes? Are they consistent? And if so, like how can we correct for that in these old databases? Because I would say, majority of the fluxes that go into the lake database, at least for diffusion, come from the edge, just because this is a easier access point to collect the measurements. I will say for like ebullition, for example, that's usually has better spatial distribution. People tend to get out to the center and the edge. But I think that's kind of going to be one of the biggest ones for lakes moving forward is like, we need more measurements in general, but if we're just collecting from a couple areas in the lake, how representative is that? And I know like from some of my own work in my PhD, like it can be quite a gradient from the center to the edge. And it also actually depends on the lake. Like I've been at a few lakes where it's actually higher emissions from the center than it is from the edge and vice versa. So this is definitely a challenge that I think will keep us field scientists working for a while.
Should I ask another question?
Yeah,
Okay, so I was curious about the modeling of the different temperature scenarios. The work that Schneider von Demling did, where he looked at permafrost thaw, also with he used different RCPs, but basically it's kind of low to extreme warming. What he found there was that, so I'm thinking permafrost carbon emissions. It's as you warm it, you're opening the freezer door. There's a limited amount of carbon in the freezer. And so in his RCP 4.5 scenario, and RCP 8.5, the total permafrost methane emissions was the same. What it was affected was the rate at which it comes out. And he found that the 4.5 it opened the freezer more slowly. And so the 8.5 opened it quickly, and it basically burned up a lot of carbon. So you see a big hump this century, like 2060, 2070. And then the permafrost carbon emissions declined because basically the carbon that was in the freezer got eaten. 4.5 just prolongs that. It's a slower release, but the amount that comes out is the same. It didn't seem like you were seeing that same response. So actually in his 8.5, it leads to drying because lakes drain. It's like the lake cycle accelerates so fast that it leads to drainage by the end of the century. Yours looked like it was still ramping up, and the magnitude of permafrost carbon was different. So I was just wondering if you thought about how these different models are yielding such different results.
Yeah,
The magnitudes of carbon.
yeah, I think that's a really good point, and it's I think everyone has a different approach, and it's great to kind of put them together to see how they differ and what we can kind of glean from both approaches. I think important aspect of our approach is that we're not technically modeling abrupt thaw. It's more these like land cover driven shifts. So if we have a landscape that goes from a wet tundra to a dry tundra, because we're applying fluxes that are from essentially these like they're averages for these land cover classes. So in some ways we might actually be missing abrupt thaw. And so if we're not explicitly modeling this abrupt thaw pulse, we're not going to get that kind of downturn. The one area where we do include abrupt thaw specific emissions is with expanding lake area. So this is where we do actually include kind of flux magnitude from recent thermokarst lake expansion. And so this is something that maybe we can update in the future is to, we don't really have a time since thaw component. This is more of a just like static, if the land cover classes have shifted because of permafrost thaw, what do those kind of average emissions look like?
I don't see any other hands up, so I'm going to ask one more question. Unless there's someone up, but
there is a question in the chat.
Okay.
But if this is like a related follow-on question, I would suggest just continuing this and then we'll get to Brian's question.
Yeah, and maybe it'll be my last one. So when lakes drain, it sounds like the emissions are thought to go down. This is a little related to that water depth question. It seems to me when at low lake levels, so both drained lakes and warm summers when the lake level's gone down and now you have this exposed mud on the margin, that's where we see the highest emissions. And I wonder if it's because the water column has been removed and so there's no that aerobic oxidation isn't happening.
Mm-hmm.
So are we getting that right in the models, in our trajectories?
Yeah, so we touch on that a little bit in our model just because when we do our land cover, like permafrost thaw-driven land transitions, we do allow some lake area to be converted to wet tundra or fens. So in a way, part of that is included in these future scenarios. Do I think we could do a better job of it explicitly including that? Yeah, and I also think from a like flux measurement standpoint, like I would love to see more field measurements from these like recently drained like lake basins. Like I know there's some that we have like older drained lake basins, but I do think that's a little bit of a gap in the flux literature is what are the emissions? Because I agree, and I think it does make sense that you can have a trajectory of higher emissions, especially if these lakes also become vegetated and start to transition towards more like wetland ecosystems where we can see really high emissions. So to answer your question in part, like yes, we account for that in part, but it's not a focus of the future trajectories, I think, which can be improved with more field measurements of these fluxes.
Okay, there is a question from Brian, Dr. Brian Malzian with EPA. He asked, Could you please describe the major sources of anthropogenic emissions or methane in the Arctic, and how could these sources be reduced or mitigated, e.g. permafrost thawing?
Yeah, thank you for the question. I definitely focus on natural emissions of methane. My work doesn't tend to focus on anthropogenic emissions, but I know there are a lot of really great research teams that are focusing on, for example, oil and gas activity, as well as kind of legacy effects of oil and gas drilling. For example, what happens at kind of like abandoned oil and gas wells in different pumping stations. Um, so unfortunately, I don't think I can fully answer your question to the depth that you would like. But I do know there are groups out there that are using similar techniques as well, thinking about these bottom-up versus top-down approaches. And so that's an area where I think, I have this question about how can we collaborate as we move forward with these monitoring efforts. And I think one area of collaboration that I would love to see is kind of bringing these groups that are focusing on natural methane emissions and anthropogenic methane emissions in the Arctic together to kind of combine these really important sources.
I could ask if no one has any other questions.
Lauren, can I just make
Lauren, did you have something?
it was a great presentation. I just want to connect with Brian really quick because we're both at EPA. Brian, you should shoot me an email because I'm the permafrost lead ad hoc, I guess, for EPA, but we have a permafrost team at EPA and we're actually working on this exact issue. So you should email me and we can connect. This is the down and upside of having so many different folks so interested in these topics across the agencies. So I just want to make sure we close the loop on that. So thank you for the time. Kinsey, lovely. I would love to connect with you sometime. This has been great.
Yeah, so my question was, so the estimates out of this study were lower than a lot of previous bottom-up estimates. How much closer did it get to constraining with the top-down estimates? And what do you think kind of makes up that remaining gap? Just, positing. Obviously, we don't know, or else there wouldn't be a gap, but
Yeah, it does bring it closer, but I wish I would have included a figure here. It also depends on the region. So I can split these emissions into like, for example, tundra versus boreal. And we see that in like boreal regions, our estimates are a lot closer to top down, but in the tundra, they're still higher than what a lot of models do. And of course, these top down models differ. I think an important thing to think about when we're doing these comparisons is that, top-down models aren't entirely separate from bottom-up. So these top-down models also require wetland and lake maps and kind of prior estimates. And so it can be hard to say like how also these top-down models are being influenced by those maps. So are these top-down models, do they include estimates from lakes and also wetlands? What is their kind of input data that are going into it? So in the future, I would love to essentially see what can happen if we can use these BAWLD estimates as prior estimates in top-down emissions approaches, just to see. But I do still think there's potential overestimates from bottom-up approaches, and I think from our approach, this could be partially due to kind of the low temporal resolution. So we're making quite a few assumptions with just having growing season averages, and then kind of adding on these winter emission estimates, which we know can the model's really sensitive to. Like it can change the annual emission estimates by, upwards of 40% depending on what we attribute that to. So I'm quite optimistic that with these kind of monthly time steps in the new data set, we can kind of constrain this uncertainty a little bit more, especially for those winter emissions, and see how they also differ across the different wetland types as well. So I think what we're starting to see is that, is it a typically drier wetland versus a more saturated wetland has a big impact on what its kind of wintertime fluxes are. And we see kind of evidence that these kind of more drier, for example, bog ecosystems can have a higher contribution of actually winter estimates or winter emissions than these typically like really wet ecosystems that most of their emissions are coming during the summer.
Hmm. Yeah, yeah, no, I think that could be really interesting because I mean something that we're seeing at a lot of our sites is like the difference between like wet tundra versus fen sites, where in the wet tundra the zero curtain's very important for the annual emissions, and then in the fen it doesn't matter as much. The emissions just kind of fall off more rapidly, even though you still get that like soil temperature phenomenon. And then vice versa in the spring, where some of our more southerly fen sites have pretty large emissions that start immediately in the spring, where the or higher latitude sites kind of like slowly ramp up during snowmelt and then release once like thaw happens. So it's kind of curious to see how like those things you miss with a temperature relationship that can only really be filled by off-season data or non-growing
Hmm.
data.
Yeah, exactly. So kind of this kind of same approach that I feel like we went at it with growing season emissions is likely to be really important for, like you're saying, these shoulder season and these winter emissions. There's not going to be kind of a blanket response across all of these different wetland types.
Mm-hmm. Yeah. Any other questions? And Meredith, how much time do we have left? Does it go to the top of the hour or what's
It
the
does, yeah. We
okay.
can go all the way to 11 Alaska time or end it early if there's no reason to continue on.
Okay, oh, go ahead.
Hi, thanks for the presentation. That was amazing. I just wanted to ask you where is the best place to read all of your work? I found a web page in your name where a lot of the research is listed. Is that the best or?
I think my on my IARPIC profile, I think I should also have linked to my faculty page at University of British Columbia, and that should list kind of the publications. And this work is in revision and is almost published. So if I go into hiding until December, it's because I'm pushing the rest of this work out. So
Okay,
hopefully you should be able to read that soon as well. But yes, my faculty website should have all of the publications.
on Columbia. Okay, awesome. Thank you.
Just had a follow-up kind of big picture question. Um, I know it'll probably be spatially heterogeneous, but which direction do you think it might go as far as wetland expansion or drainage, as far as those scenarios? Do you have any sort of inkling or thinking behind that?
That's really tough. I mean, I think there's a lot of really great work coming out when it comes to lakes that the like kind of glacial history and like subsurface like geology is really important. And it seems like of the work that's coming out, we actually might see a lot more lake drainage than expansion, depending on the area, which I find really fascinating because kind of when I came into the field, it was I kind of had this idea that lakes and wetlands were just going to expand and it was going to be a really wet Arctic, which I do think is going to be true in a lot of regions. But yeah, it's hard to say. And I think another thing I didn't really touch upon a lot in our model is that we think that the reason why the wetland emissions are not as sensitive to temperature as other models have shown, especially process-based models, is because um, in our empirical data set, so in BAWLD flux, in the BAWLD methane flux data set, we also see this relationship where with increasing mean annual temperature, we're seeing actually lower water table in the data set. So where we would expect higher emissions because of this relationship between like microbial activity and temperature, what we actually see in the data set is with higher mean annual temperature, you're actually getting slightly drier conditions. At least that's in our available data set, which was surprising to me, but I think is going to be really interesting, especially as kind of new land cover products and kind of future scenario products come out.
Are there any other final closing?
I have one question. Just curious, I know you're not necessarily focused on detailed drivers or mechanics of what's um, driving fluxes, but I'm curious about organic matter quality across these different ecosystem types. It seems like there's a lot of diversity of, PD organic settings and maybe mineral associated carbon and other settings. Just curious how that mitigates some of the variance in flux and how that interacts with these physical temperature, drainage, moisture drivers.
Yeah, definitely. So the wetland and lake classes were developed with this organic matter question in mind. For example, like our designation between like marshes, which are considered more minerogenic soils, compared to bogs, which are more peaty materials. So that's how we define those. It also really comes into play, I think, even more so for the lakes. So we have kind of three main kind of lake sediment organic matter categories. So we have what we consider like organic rich, which are like these small kind of like peatland ponds, areas that are really peat dominated. We have Yetama lakes and also kind of more post-glacial glacial lakes, which we consider more minerogenic and organic poor. So that's really where kind of the influence of our organic substrate comes into play is within those class designations. Within the data set, like I also looked at drivers such as organic layer depth, which didn't actually come out in our data set for as significant. So it didn't really matter if it was organic layer depth of 40 centimeters versus 100, at least in the select sites that we have. But we didn't also include, for example, percent carbon or percent nitrogen, some of these other soil characteristics that I think could be important. And really, we're reliant on what we were able to extract from available studies when it comes to kind of description of soil organic matter and kind of landscape level organic history. So it does take into account a little bit, but not at that detail I think that you're asking about.
Cool. Thank you.
All right. Well, if there's no further questions, thanks to those of you that stuck it out all the way till the end. And thanks again, Kenzie, for your presentation and for joining us today.
Cool. Thank you, everyone. And thanks so much for having me. Thanks, Kyle and Meredith, for organizing and for all the support. Yeah, thanks everyone else for coming.
Thanks so much. The presentation will be posted probably this Thursday, the recording. So all are welcome to share it.
Thanks, everyone.
All right. Bye.